Okay, so as I mentioned in the last lecture, this lecture is purely for a big example. This is a very real life related. You can just think about it. How can you use the information you can find from a table and also a handbook and do some interesting estimation of what happens across the body right now, what happens in our capillary wall. So these are a very useful and realistic applications, and you should learn to do this type of exercise if you want to solve some problem as an engineer in the future. So this is considered transport across a capillary wall. So you consider a small water soluble but lipid insoluble solid such as glucose. That means those type of solute can only go through the pores across the capillary wall. We want to consider their transport across the endothelial cell membrane and then transport on the other side. Although this is possible, and there are membrane channels that allows glucose to go in and out. But for the purpose of this calculation, and time scale of the problem, we are not considering those type of scenario. Let's just assume we are considering a solute that goes through the pores in the membrane, in a cylinder capillary wall. The solute has a diffusion coefficient in water at body temperature. Given you the diffusion coefficient, they give you the molecular diameter, and the average concentration of glucose in plasma is approximately 5 micromole per centimeter cube. So they give you the concentration in one side, and it assumes that all the glucose transported to the extracellular space is consumed. That means on the other side of the capillary wall, you assume its concentration is 0. The tortuosity of the capillary walls is given. It asks you the rate of transport by both the transportation mechanism, like convection and diffusion across the capillary wall. And the dynamics viscosity is given. So the filtration just means convection. Okay, so let's recall from last time. We have equation ma dot, that is mass transport rate. This is Ca 1 minus sigma Q plus Cm S delta sigma. Now the first term is the mass transfer due to filtration. So the first term we can write it as m dot filtrate. So this is a dot filtrate. The second term is due to diffusion. We need to figure out each of these and the sum of these. So what do we need? We need a Ca tutor within the membrane. That's easy to get because we have the concentration on the two sides of the membrane. We need a sigma. Okay, now you need to think about it. What tools do we have to get a sigma? The reflection coefficient. We have Q. Okay, how do we get a Q? Recall that in an early lecture for the filtration across the capillary wall, if you recall that we had an example. How did we solve for Q? And the PM, okay, how do we estimate the PM in early lectures? S, how do we obtain the surface area of the membrane? Delta C is something easy because it's just the concentration difference. So we need to get this term by term. First, maybe let's look at the sigma. Well, the sigma expression, if we use the theoretical model we just discussed in the last lecture, the A is the radius of the solute. I is the radius of the what do we call the pores? Okay, so let's see. It gives us the molecular diameter is, so A is 0.41 nanometer divided by 2. And I is the radius of the pore. And it gives us the height in the table. So it's just 7 nanometer divided by 2. You can use it as a radius. Although for a slit rectangular pore, you cannot really define diameter or radius. However, for the purpose of this discussion, when you consider the ratio between the size of the solute versus the size of the pore, it is sufficient for this purpose. So A divided by R is these two ratios. And if you plug in, you will get sigma. It's a pretty small number. Okay. Now let's see, we still need to collect a lot of things. Let's do it one by one. We can figure out what's the hydraulic conductance. Because we need the hydraulic conductance to calculate the Q. Hydraulic conductance for a rectangular pulse is epsilon h squared 3 mu tau L bar. Okay, epsilon equals to, let's see, we have pore fraction from the table. So it's 0.001. H squared, H is the half height of the pore. So now the pore height is 7 nanometers, so H, then H itself is 3.5 times 10 to the minus 9 meter. And it's 3.5 nanometer. And then we have mu. Mu is 1.2 times 10 to the minus 3 Pascal second. The tortuosity is 2. And the L bar is the membrane thickness. So this L bar is the length of the rectangular pore. The pore embedded in the membrane is the membrane thickness. So let's see, membrane thickness. It's a wall thickness. It's 0.5 micron. So 0.5 micron equals to 0.5 times 10 to the minus 6 meter. So you put all of this number into it, you will get LP equals to 3.4 times 10 to the minus 12 meter Pascal second. I strongly suggest you pull out your calculator and verify this. Because there are a lot of mistakes that the people usually make during the calculation. They may forget to square something, or they may not have the conversion like from nanometer or micron to meter correct, or they may have like the index being wrong. So you need to practice on this in order to make sure that you can do this fluently when you need. Okay, what else? In order to calculate the Q, so what do we want to find with Q? Q is equal to LPS multiplied by delta psi. Which is LPS multiplied by delta P minus the delta pi. So we need LP and we also need S. So what is S? S is the surface area of the capillary wall. So S is surface area would be pi multiplied by the diameter of the capillary and the length of the capillary. So pi multiplied by the diameter of the capillary. The inside diameter is 10 micron. 10 micron is 10 times 10 to the minus 6 meter. And L is the length of the capillary, which is 0.1 centimeter. So it is 0.1 into the 10 minus 2 meter. So let's see what it will give us. It will give us 3.14 times 10 times 10 to the minus 8 meters squared. Okay, now we are ready to figure out Q. So LP is 3.4 times 10 to the minus 12 meter Pascal second. Area is 3.14 times 10 to the minus 8 meters squared. Okay, let's figure out the pressure. The delta pressure difference, we use the average pressure. So it's 7.3 plus 3 millimeter mercury. That's a delta P. And this delta pi is 28 minus 8 millimeter mercury. Now to convert a millimeter mercury to Pascal, we have 133.32 Pascal per millimeter mercury. And that gives you volumetric flow rate, 4.27 times 10 to the power of minus 18 meter cube per second. It is 1.54 times 10 to the minus 8 centimeter cube per hour. All right, we got a Q. We also got sigma. So that means we are ready to calculate the filtration component of the transport. That's good. So let's get NA of filtered, which is CA delta 1 minus sigma Q. CA delta is the average, so we have 5 plus 0 divided by 2 micromole per centimeter cube. 1 minus sigma is 1 minus 0.001, sorry, 0.0152. That's sigma. Let's verify it. It is, what is our sigma? It's here, yeah. And Q, we just found it. It is 1.54 10 to the minus 8 centimeter cube hour. So you can see centimeter cube cancels out. So you get 0.79 next time 10 to the power of -8 micromole power. Okay, good. Now let's see. We need to figure out the diffusion part. We needed to know PM and let's see what is PM. PM, recall, from a theoretical point of view, you can calculate it by using D plasma divided by L bar. This multiplied by AP divided by S, which is the membrane porosity, then K omega R divided by tau. Okay, we have several things to figure out. What is D plasma? D plasma equal to EAB, and then you count for the viscosity, so the viscosity of water divided by the viscosity of plasma. We also discussed it in some previous lecture multiple times. So DAB is the viscosity. Sorry, DAB is it's the diffusion coefficient in water. So it's 0.93 10 to the -5 centimeters per second. So it's 0.93 times 10 to the -5 centimeters squared per second. Viscosity of water is at body temperature, it's 0.691 centipoise. Viscosity of plasma is 1.2 centipoise. So it gives you 0.54 times 10 times 10 to the -5 centimeter squared per second. We also need a K multiplied by omega. K multiplied by omega. We also had the equation which we call the Rankins equation. It is 1 minus lambda squared multiplied by 1 minus 2.1 plus 2.09 lambda cubed minus 895 lambda fixed. This is, if you forget, you can check. Rankins equation. Lambda is the same thing, A divided by R. So if you use this A divided by R, you get K omega R is 0.7776. Now you are ready to calculate plasma membrane permeability. So it is D plasma is 0.54 into the -5 centimeters squared per second. Now the L is again the membrane thickness. Membrane thickness is 0.5 micron. So it's 0.5 times 10 to the -4 centimeter. Since we have been using centimeter in the diffusion coefficient, we can keep on using centimeter. So AP divided by S is the porosity, the O1, and the K omega R we just calculated is 0.7776. divided by tau tortuosity given in the problem statement is true. So you get a membrane permeability 4.2 times 10 to the minus 5 centimeter per second. So recall that membrane permeability has a dimension of velocity. So you check that you got it correct. Okay, now we can calculate our diffusive transport. M dot A. Diffusion is equal to Pn, yes, multiplied by delta Cn. Okay, let's plug in the number. And we figured out is 4.2 times 10 to the power of minus 5 centimeter per second. Surface area, we just calculated over there. So this number, it's 3.14 times 10 to the minus 8 meter cube. Okay, if you want to convert to centimeter, it's minus 4 centimeter, sorry, not a cube, centimeter squared. Say 4. And delta A is, this is 5 micromole per centimeter cube, because on the one side it's 5 micromole per centimeter cube, on the other side it's 0. Then you multiply this out, you can see the volume cancels. So indeed we got the correct dimension. It gives us 654 times 10 minus 8 micromole per second. It's the same as 2.36 times 10 to the max minus 4 micromole per hour. Okay, we got the two. Good. Let's just sum up them together. NA dot to NA filtration plus NA dot diffusion. Just put these two numbers together. Just compare the order of magnitude. One is on the order of minus 10 to the minus 4. Another is on the order of 10 to the minus 8 micromole per hour. So you can see that the minus 8, the first term is negligible. It's not going to do anything. So that means the filtration barely contributes to anything. The process is diffusion dominated. So now you can tell, okay, the transport of glucose across our capillary wall is mainly due to diffusion, not due to filtration. And then we can check the packet number to verify this. So packet number, see if this is true. Packet number is 1 minus sigma multiplied by Q divided by P and multiplied by S. So let's see, 1 minus 0.0152 multiplied by Q, 4.27. And then we divide by Pn, area. You can check it indeed is a dimensionless number. Wow, then the number is very, very small, much smaller than 0. It means the diffusion dominates the transport. So the conclusion is the diffusion dominates the transport. Okay, so that's this example. I hope you can go through it multiple times on your own so that you know exactly what is involved. How do we get started from this equation for MA dot and then figure out what do we need term by term and how do we put things together.